Jen-Tzung Foundation Cheng Taiwan. This is a joint work with my student, Chien. This is outline of this presentation. Includes introduction, speech recognition, Approximation, Sparse Coding, and I will present both sparse Markov models. Then I report experiments and give conclusion and future works. As we know, Markov models have been successfully developed for speech recognition and many other applications. People usually use mathematical estimation to estimate Gaussian mitchell models. But this is easy to get overfitting problem. Especially speech data usually connected to heterogeneous environments with noise interference, with neighboring problem, with sparse data problem. So model regularization is an important issue for speech recognition. In speech recognition system, we extract speech features from speech signal. Usually, we extract male frequency capture coefficient to represent a vocal tract of human body. Then we use acoustic model based on Markov models to perform a syllable level matching, and then we obtain a syllable lattice. Then we perform sentence level matching based on language model. Then finally we obtain a recognized sentence. And we usually use this left to right without skipping Markov topology to model the behavior of speech utterance. We use transition probability to model the transition from one frame to the other frame. And this is a doubly stochastic process. And we usually use this formula to calculate log likelihood function. Here X is a bunch of speech sentences, maybe from a speech corpus, and we calculate likelihood for individual speech frames and connecting by the transition probability A. And for each observation in a hidden Markov model state, we use Gaussian mitchell models with mitchell weight, omega, and the mean, mu, and the precision match R. And the motivation of this study are given below. We are challenged about this existing hidden Markov models are good enough for acoustic modeling, and is Gaussian mitchell suitable to represent speech features corresponding to an hidden Markov model state? Can we change the model structure? And we are wondering how can we share the model parameters for different Markov models, and how can we enhance individual state information for one state? And we are questioning about how can we build a regularized model for speech recognition. So recently, I and my colleague IBM T.Z. Watson, we presented a very high-performance model called Bayesian sensing hidden Markov models. This model will represent data by a bunch of basis vectors. We don't use a lasso optimization. We follow up relevance vector machine. We use a Gaussian distribution to represent weight, sensing weights. And in this work, we estimate a state-dependent compact dictionary. And we represent a reconstruction error between observation and the basis representation using a Gaussian distribution with zero mean and the precision Rs. And this Gaussian distribution is easy to disperse because we have a gamma distribution for the precision parameter. And this alpha parameter is a kind of ARD, automatic relevance determination. And in the Bayesian sensing hidden Markov models, we have state-dependent dictionary, we have state-dependent precision matrix. In the modeling error, we have state-dependent ARD. So the all the models are designed for the hidden Markov models, and this is almost the best performance in speech recognition so far. It's very state of art. And in this work, we are thinking a different way. We are thinking of group sparsity in hidden Markov models, and we try to represent a speech feature by groups of basis vectors, and we use truly sparse prime. We use a Laplacian scale matrix distribution, and we use Bayesian approach. We use map estimation. Let me first introduce this Laplacian sparse coding, which just propose less NIPS. Using this sparse coding, Laplacian scale matrix distribution is used. This distribution is obtained by eta inverse times u. Eta is a gamma distribution, u is a Laplacian distribution. And because Laplacian and gamma are conjugate, so the marginal distribution marginalizing eta is a Laplacian scale matrix distribution with this form. And this distribution is even sparser than Laplace distribution. So when we use this distribution for sparse coding, we represent a single pattern, just single sample. So we estimate parameters, we estimate sensing weight, we minimize upper bound of negative log posterior distribution. And because of the latent variable eta in the estimation, so EM algorithm should be applied. In E step, we estimate best variational parameters, and in M step, we find a weight. And we can formulate this optimization as a weighted L1 regularized objective function. In this weighted L1 regularization objective function, this is some square error of the modeling. This is a kind of lasso, but with a weight. So here is a weighted lasso. It's a kind of weighted lasso with the sparsity control parameter eta, which can be calculated in closed form by this way. And the grouping of the basis representation can be done for the non-overlapping group case. It can be also done by for the overlapping groups. And this sparse coding is designed for the representation of single pattern. But in speech recognition and the many other applications, we deal with not only sample, we deal with a bunch of speech corpus, a large corpus. We collect a lot of data. We want to use hidden Markov model to organize the state information and the individual segment. It's a kind of segmentation and labeling in the work. And in this idea, in this paper, we just simply use two groups of basis vectors to represent speech features. One is called common basis. The other is called individual basis. Common basis here are used to represent speech features over different HM states. And the individual basis here are used to represent speech features within a state. So we want to use some common modeling and the individual modeling to enhance the hidden Markov model for speech recognition. And this is the model is quite simple. We have two groups. Phi C is a common basis. Phi SI is individual basis. And here we introduce Laplacian scale matrix distribution to force the sparsity in the representation. And we have two sets. We have four sets of parameters in the group sparse hidden Markov model. One is weights for the common basis, weights for the individual basis. and also common basis and the individual basis. We have 4 sets of parameters to be estimated. And we use a map. We maximize we minimize minus log posterior. It's maximize posterior. It's the same thing. And here we introduce prime for the weight to be Laplacian scale Mitchell, and we use Gaussian to represent a dictionary for 2 groups of dictionary. And we use an EM algorithm. We use in the E step we calculate auxiliary function. In the auxiliary function here, R is a calculation over all the samples, all the data corresponding to the cluster C. So when we optimize this auxiliary function to perform M step, we take differentiation with respect to W, and we find this solution. This is solution of weight for the common weights. This is solution for the individual weight. And we can see for the weights for the common basis, we have a C index here. Is a count of all the sample corresponding to the cluster C. But in the individual sensing weight, we don't have this C index here. And when we estimate basis vectors for common basis, we do the same thing, but here we only concern common basis, and here the calculation of auxiliary function is also done for all the samples corresponding to the cluster C. Here the key difference in hidden Markov models, we have this posterior probability. This is occupation probability. Means the probability of the sample given the current estimate. So with this probability, we can estimate hidden Markov model parameters. And in calculation of this common basis, we take differentiation and set it to 0, and we find this corresponding dictionary solution. Also here we can notice in calculation of common basis, the summation here is all the sample corresponding to cluster C. And for the individual basis, we don't have this term, but we have similar form of the in the solution. And here we can say basis vectors from the common group and the basis from the individual group are used to spend the subspaces to represent we say interstate variations and the intrastate variation respectively. And in implementation of speech recognition, we need to use a Viterbi algorithm to perform dynamic programming to find the base state sequence for the input speech utterance. And here is a graphical model for each sample xt, xt minus 1, xt plus 1. We have parameters w, phi. Phi c is common, phi st is state dependent, and the state is transition time by time. And the eta is a control parameter for the sparsity of w. This is a flowchart used to implement a group sparse hidden Markov model for speech recognition. This is training path, this is test path. In training path, we have initialization, and we estimate parameters based on map. And we check convergence. Finally, we estimate group sparse hidden Markov models for testing to find the recognition result. And in our experiment, we perform noisy speech recognition to evaluate group sparse hidden Markov models. Aurora 2 is a very standard test a task for speech recognition. It's an English connected digit in different noise environments. We have two cases of training. One is multi-condition training, including noise data in the training data when you train the models. The other case is we don't have noise data, just use clean data to train clean model. But the test data, we have noise data to be tested. And we train 39, so the dimension is 39 MFCC-based feature vectors. This is quite standard in speech recognition, including 12 MFCC and the log energy and their first order and the second order derivatives. And in test data, we cover different noise type and different SNR. And for each noise condition, we have 1,000 speech sentences. And then in our experimental setup, in standard hidden Markov model, each word, each digit is represented by 16 states and 3 Gaussians. And the hyperparameters here, we select from validation data, and we compare group sparse hidden Markov model and the standard hidden Markov model with a comparator model complexity. And the recognition rates are average over different noise types. And I report results here. This is a different accuracy in different SNR by using clean training and multi-condition training. In clean training and multi-condition, we have baseline HMM and group sparse HMM. And we can see here we don't perform any speaker adaptation or any other noise robust technique. We just perform the very baseline hidden Markov model and the group sparse hidden Markov model. And we can see in multi-condition training, we can see noise data is included in the training, so performance is higher than clean training. And we can see the higher SNR and the higher accuracy. And the most important thing, we got better performance than baseline hidden Markov model. It's a significant improvement. So this is conclusion and future work. In this book, we present group sparse hidden Markov models for sequential pattern recognition, not just only for one sample coding, not just only for the we can apply for recognition. And we build 2 groups of basis vectors for represent speech features better than baseline. And the Laplace scale mutual distribution was introduced for sparse representation. And in the future, we are thinking how to determine number of bases in different groups is an important issue, and we haven't investigated yet. And the other noise robust method can be combined to improve the whole performance. And in the future, we are conducting a larger scale speech recognition task. Yeah, this is my presentation. Thank you.
Questions for the speaker?
So, if I understand correctly, you learned both baseline HMM and your HMM using expectation optimization algorithm, right?
Right.
So, there are like some other algorithms to learn HMM that were developed in like last, I guess, 5-10 years. So, did you plan to check these? Because there are some pretty good results.
You mean some other approach using based on?
So, estimating the parameters of hidden Markov model from the observations. Because expectation maximization is a lot of optimal algorithm, right? So, there's some other algorithm how you find the HMM parameters using through the training.
We haven't investigated this direction, but I believe is this is in optimization society, people are using EM algorithm. Don't maybe not think too much on the other issues in the optimization problem. We don't investigate this issue in this study. Yeah, maybe it is good issue to be solved.
Yeah, I'm just curious how these new algorithms could work in this the speech recognition task. Because, well, I mean, it's well known that EM is good, but it has limitations. So,
Yeah.
it might be interesting.
Yeah.
I have a question. So, in your model, you said you use a Bayesian model, but eventually, if I understand well, your algorithm is you're modeling probabilistically the states, but you are solving each of the decomposition on the dictionaries via solving an optimization problem. Right? So you don't model the latent variable, the latent decomposition coefficients probabilistically. Is that right? And would you think it would be possible to do the same thing with Bayesian modeling alpha probabilistically?
I think the latent variables here.
So you've got at each stage you've got a dictionary feed,
Right.
And you've got the coefficients W.
Right. Right.
Right now, in the first formulation that you presented, W was modeled in a Bayesian way, right?
Right.
But here it seems that you're maximizing, you're solving, right?
I don't think too much on the. Here with data variable, we only have a state. We have nature component in the model.
Sure.
Sometimes we can say the control parameter theta is also a data variable. So data variable can be solved in different way. Actually, in the whole hidden Markov model contain different data variables. Yeah, not just the data variable for sparse coding, but also data variable for mixture components. Yeah, for states, they are all latent. Yeah, but I don't think too much on how these data variables affecting the whole model. I don't investigate too much on this direction.
Okay, so thanks to speaker again.